Today, we're going to be talking about plotting and about mortgages again. I should say, as I look at my title slide, it occurs to me that there's a certain ambiguity in the title. I want to make it clear this lecture is not about how the home loan industry plots to take advantage of potential homeowners. In this segment, we will return to the mortgage example used a couple of lectures ago and create some plots designed to shed some light on ramifications of different kinds of mortgages. Along the way, we'll learn a bit more about both plotting and classes. As a reminder, let's look at the hierarchy of classes developed in the previous lecture. At the bottom, even though I'll draw it at the top of the hierarchy, is class object, the class upon which everything in Python is built. We then looked at mortgage as a subclass of object. This was an abstract class whose only purpose was to be included into other classes. We then looked at a subclass of mortgage called fixed, another subclass of mortgage called to-rate, captured the notion of a variable rate mortgage, and a subclass of fixed as well, fixed with points. One of the disappointing aspects of the lecture in which we introduced mortgages was that we used text to try and illustrate the behavior of the different types of mortgages. But now we know better. We know how to use plots. So we'll use those to do a better job of it. We'll start by looking at a class called mortgage plots. This class is an example of what's often called a mix-in class. Think of it as a class kind of like mixing Oreo cookies into your ice cream. Up to now, we've talked about classes as types and subclassing as a mechanism for defining subtypes. So, for example, we might say that fixed is a subtype of mortgage and fixed with points a subclass of fixed. This is indeed the primary use of classes in well-organized Python programs. Occasionally, however, it is convenient to use the class mechanism to bundle together a set of related functions that don't constitute a type, as we have done here. I'll come back to the details of the class in a moment, but first let's look at how it's incorporated into our overall program. Come over now and look at the code. I've reproduced the code that you saw in the lecture on classes, but I'm going to modify it now. I'm going to use the multiple inheritance mechanism of Python to take mortgage and change it so that it not only incorporates object, but also incorporates the class we just looked at, mortgage plots. Now, if we think about what this means, we can go back to our previous class hierarchy, and we can think, okay, what we've done here is now mortgage not only uses objects, but it uses mortgage plots. We call it multiple inheritance because mortgage now has two parents, and it inherits attributes from both object and mortgage plots. We should be careful, though. This is an inheritance graph. It's not a subtype graph, i.e., mortgage is a subtype of object, but not a subtype of mortgage plots. Multiple inheritance is sometimes useful, but it can also be dangerous. That's a terrible looking danger. Let me write it again. Danger. Fortunately, there are some rules of thumb that help you stay out of trouble when using multiple inheritance. Consider the case where class A has superclasses B and C. It should feel comfortable to say that A is a subtype of at most one of B and C. The goal is to ensure that the two lines of code, class A, B, C, and class A, C, B, mean the same thing in the context of the program. Roughly speaking, the guideline boils down to saying that if little a is an instance of A, the text a.name, name is some method of class A, should resolve to the same attribute irrespective of the order in which the interpreter searches the namespaces associated with B and C. By convention, it is convenient to list the class that implements the supertype last, as we've done over here for class mortgage, as we look at the code. Now let's go back and look at the code for mortgage plots. When a figure contains multiple plots, it is useful to produce a key that identifies what each plot is intended to represent. The methods in class mortgage plots use a form of pylab.plot that does that. So if we look at it over here, what we'll see is that in addition to telling it what to plot, we're giving it a style. Remember, we looked at that last time. That includes things like color and line type, or line style, and a label. We have not looked at that before, which will be in the key. We've made both the style and the label formal parameters to the function plot payments. We'll later see how those are used. Each invocation of pylab.plot uses the label keyword argument to associate a string with the plot produced by that invocation. Recall, by the way, that this and other keyword arguments must follow any format strings. A key can then be added to a figure by executing the function pylab.legend, open close, as we will see very soon. All right, now let's look at two functions, plot mortgages and compare mortgages, that are used to actually generate interesting plots. The function compare mortgages generates a list of different mortgages and simulates making a series of payments on each, as we saw in the earlier lecture. It then calls plot mortgages to actually produce the plots. So if we look at compare mortgages, it takes a principal amount, the years, information about the rates, the variable rates, etc., and various kinds of things. Nothing very different from what we saw in the previous lecture when we were testing our different kinds of mortgages. The function plot mortgages is more interesting. If we look at it, it takes as arguments morts, kind of a bad name, but stands for it will be a list of mortgages, and an amount. Then there's a constant styles here, which will be used to plot each mortgage in a different style. So we have a blue line, a red dotted line, and a green dashed line. We then start a figure called payments. Notice that payment starts at 0, and then we're also going to have cost starting at 1, which will also be used for figures. So we start a figure called payments. We put a title on it, monthly payments of different, etc. Label the X and Y axes as we're supposed to. We then go to a new figure called cost. I could have written 0 and 1, by the way, but I thought by calling them payments and cost, it would help me keep straight in my head what each figure was supposed to represent. Then it gets a title and labels. Going on to look at the rest of that function, we then look at each mortgage for I in range len of morts. We create a figure called payments, a payments figure, plot the payments. We then go to the cost figure, plot the total paid, or the cost. Notice that each time we do that, we pass in a styles sub I, and it's this I. And what that's telling us is that for each mortgage in morts, we'll get a different style. The other thing you haven't seen before, we have the legend command. You can do it with just open close, in which case it will be put in the default location. Just to show you don't have to, I said I want this figure in the upper center, and I want this figure in, well, now I'm saying I don't know what's best. I'm going to let Pylab figure it out for me, put it wherever it thinks is best. Okay, now let's look at what happens when we call these functions. All right, I'm now going back to the code. This invocation of compare mortgages should shed some light on various types of mortgages. Let's see what happens when we run it. But let's put in a pylab.show, because otherwise we won't see anything. Uh-oh, Something has gone wrong, and in fact this was not something that I intended to go wrong. Let's look at it and see if we can figure it out. Phooey. Object with a capital O. We know better than that. Object should have a lowercase. So let's go back to where we were playing with it. Should be in the class mortgage. And let's just make that a lowercase o. Should have known I was in trouble when it didn't turn that fuchsia color when I typed it the first time. And now, hopefully we'll run it and we'll get some plots. I feel better. Okay, so let's look at them. So the first plot we have here shows the monthly payment of different kinds of mortgages. Notice that the key has appeared in the upper middle as I asked it to. Maybe that wasn't so smart because you'll notice that it's obscuring part of this plot here. Still, I should fix it, and next time I run this I will. Maybe I'll just let best and let Python figure it out for me. Okay, what this plot makes clear is how the different mortgage payments vary over time. We can see the fixed doesn't vary. The fixed with points doesn't vary. But of course, the mortgage with two rates varies quite dramatically. It doesn't tell us much about which is the better mortgage, but perhaps this figure will. Look at Python. It cleverly put the legend where it's out of the way. So what this tells us is that over the long haul, the winner seems to be the fixed with points. Down here, if I hold on to the mortgage for 350 months, I save a fair amount of money with this mortgage over the other two. But suppose I don't think I want to hold it 350 months. Suppose I think I'm going to sell my house in 50 months or 100 months. Well, remember we have this zoom button. We can now go and look down here at the lower part of it and see it in much more detail. And then we notice, well, depending upon how long I want to wait, different mortgages have different values and they cross over at different places. Looking at where the curves cross suggests that if one plans on holding the mortgage for a very short period of time, the winner is going to be the variable rate. Somewhere out here around, say, maybe 62, 63 months, these curves cross, and now the fixed with points becomes the winner. If one is not interested in a variable rate mortgage, then we can look at this crossing point here, which tells us when we pay off the points. All in all, I'm not going to recommend a mortgage to you, but if you happen to be in the market, you might want to use this software to look at which mortgages will work best for you.